Hugo. Thank you very much. Thanks, everyone, and thanks for the opportunity to speak. My name is Will Probert, and I'm a researcher at the Big Data Institute at the University of Oxford. And I'm going to be talking about some techniques that we've been using called reinforcement learning that sort of capitalize on the wealth of simulation models there are available to generate context-dependent control. So control that can change throughout an outbreak. This is very much a collaborative piece of work. If I can get the slides to move. This is very much a collaborative piece of work between the UK and the USA. This work was started when I was a postdoc with Mike Tildersley at Warwick University, and also with Matt Ferrari and Katrina Shea at Penn State. This also includes Matt Keeling at Warwick, Mike Runge at the US Geological Society, Chris Fonsbeck at Vanderbilt University, and I'd like to also acknowledge my current boss, Christoph Fraser at Oxford University, for support for travel and accommodation to attend. So I wanted to start by pointing you to, if you look at page 72 of a report by the Department of the Environment, Food and Rural Affairs, DEFRA in the UK, on their report called the Contingency Plan for Exotic Notifiable Diseases of Animals in England, you get this diagram, this flow diagram that they call an algorithm, and it's for when to use emergency vaccination in a foot and mouth disease outbreak. You can't really see it here, but at the top in diamonds are questions, and the idea, excuse me, the idea is that you successively answer these questions. You start in the top left-hand corner, and they're questions such as, can the disease be eradicated using stamping out only? And you successively ask yourself these questions, answer these questions, and they lead to a recommended control action at the bottom here. Things such as stamping out of infected premises and dangerous contacts, or stamping out with vaccination to live, and so on. So what this is really is what I'm going to call a policy. It's a rule set that's saying if you're in this state, then this is the recommended action. In this situation, it's a mapping of the state of the country in regards to its ability to respond to an outbreak into recommended actions. And this is a very sensible approach. Almost every decision-making problem that we deal with is really a context-dependent or a state-dependent control problem. When I was deciding this morning whether to bring my umbrella or my jacket, I looked outside and I said, oh, okay, it's raining a little bit, but it's quite warm, so I'll leave my jacket at home and I'll take the umbrella. It was a state-dependent decision that I made. It depended on the state of the weather at that point in time. So this is something that, this is a really sensible approach, and it's something that we know is the case. It's a sort of, it's a no-brainer that we know that this is how we should deal with foot and mouth control. Some recent work that we've looked at, looking at retrospective analyses of the Miyazaki outbreak in 2001 and the UK outbreak in the Miyazaki outbreak in 2010 and the UK outbreak in 2001, showed that control choice recommendation was really driven by the locations of the infected premises. So it was a state-dependent decision. The best course of action was dependent on where those locations of infected premises were. So this control algorithm, this policy for choosing whether to implement emergency vaccination or not, is only for one time step. It's only taken at the start of the outbreak. And we might want to look at decisions that can change throughout the course of an outbreak, so on a much finer temporal scale. And the questions that we ask ourselves that define the state of the system or the state of the country in regards to its ability to respond are just yes-no questions. But we know that there are a lot of factors associated with foot and mouth disease control that influence what's the best course of action, and they're continuous variables. They're not just yes-no binary variables. So we wanted to generate something like this, an algorithm like this, that's at a much more nuanced scale. Because we know, if history is a guide, that control actions do change through time, and they can change through time. So the question is, how do we generate these context-dependent control policies? So what do they look like? Well, let's just look at a cartoon to begin with. So consider what such a policy might look like. I've drawn it here with two state variables. One along the x-axis is the area of the outbreak, and one along the y-axis is the number of infected premises. And you could consider that these might be two things that influence how you choose what's the best action to take throughout the course of an outbreak. And I've coloured this area with just 3 different colours, showing potentially 3 different control actions that might be the best control action to take when the outbreak is in that particular state. So the outbreak may progress through time, and as the outbreak progresses, it traverses a trajectory across the state space, and then the control action, the recommended control action, may change as well. And so how do we really generate these state-dependent control policies? The approach that we've been using is using a suite of techniques that come under the header of reinforcement learning, and one particular flavor of that is called epsilon soft Monte Carlo control. And I guess you can think about all these algorithms as kind of a wrapper that wraps around your stochastic simulation model. So you can take your favorite simulation model, whether it's ADAS or NADSIM or DADS, and you can wrap a reinforcement learning wrapper around it. And the reinforcement learning algorithm really just treats the simulation model as a kind of sandbox for playing around with different control actions and finding out what's the best action to take in every particular state that you might be in. So consider a simulation model here in this grey box in the middle. And we give it a whole bunch of, we parameterize it and give it a whole bunch of seeding conditions, and we run a simulation. And at the end of that single simulation, we keep a list of which states that we've been in, so how the outbreak progressed through time. I should just reiterate that we're allowing this simulation to change control through time, and initially we don't mind what it chooses. It can just choose random actions. So we simulate an outbreak, and we record the states that we were in, so how the outbreak progressed, the actions that we took when we were in, or that the algorithm took when we were in those different states, and the realized outbreak duration that was simulated, or some other measure of success that we might be using, that we might want the algorithm to optimize. And then we look back through all those different states and the different actions that we were in, and the algorithm records what was the realized outbreak that we saw when we took that action in that particular state. And then this is done many, many thousands of times, and we build up an idea of what's the value of taking a particular action, what's the realized outbreak of taking a particular action when we're in a particular state. And the trick with the reinforcement learning algorithm is that it looks at the history of simulated outbreaks, and most of the time when it's in a particular state, it chooses a particular action that has, from the history of all the simulated states, maximized or minimized outbreak duration, or optimized whatever objective you're trying to optimize. But a small proportion of the time it chooses a random action. And this is just the algorithm learning. So you can think of your simulation model as exploring the state space of all possible outbreaks that you might see, and you can think of the reinforcement learning algorithm as exploring the range of different control actions that you might be able to take in those particular situations. So I just wanted to give you a very quick example, and sorry to jump back out, but just to give you a very simple example of this algorithm working. So this is a very simple decision-making problem called Windy Grid World, and the basic system is in the top left-hand corner. So imagine you're this little blue dot jumping around this state space, and the decision-making problem is that you want to go from that red square on the left to the green square on the right. That's the decision-making problem. And at each time point, you can go up, down, left, or right, and you've got to optimize, you've got to minimize the duration taking you from that red square to that green square. The difficulty is you can't just go straight across. These blue lines, this is why it's called a windy grid world problem, these blue lines are wind, essentially. So they push the little blue line, the little blue dot up if it moves into those boxes. So really the optimal solution is to sort of go along, get pushed up, go back down, and come back to the green square at the end. So you can see that, so this is a problem that can be solved with reinforcement learning, and you can see that the blue dot is sort of choosing random actions, because it doesn't have any idea of what's the best position to go to, because it hasn't got to the final stage yet. But once it gets to the goal state, it'll repeat the simulation again, and it'll get a reward for getting to that goal state, and it'll use all the information it has from the previous simulations to improve its decision-making ability. So if I jump to halfway through here, you can see that it's, or potentially not, maybe I need to jump a little bit further. You can see that it's getting to the goal state, and it's improving its ability to get there in a shorter period of time. So this algorithm is learning it's learning a decision-making task using a simulation engine that we've given it. Whoops. So we've been applying this to foot and mouth, the control of foot and mouth in hypothetical outbreaks. So we looked at a random landscape of about 4,000 farms using a transmission model that's previously been published by Tildersley in 2008 and Keeling in 2001. And we wanted to construct a policy that used two state variables, one using the area of the outbreak and one using the number of infected premises. The objective that we gave to the reinforcement learning algorithm was to minimize the outbreak duration, and we gave it 4 different actions that it could implement. It could implement suppressive culling at 2 kilometre or 4 kilometre radius and vaccination at 2 kilometre or 4 kilometre radius. And it could change that action every 3 days. And I should note that these algorithms, you could penalise them if you didn't want them to change very frequently. And there were constraints in the simulation. There was a global limit on the number of carcasses that were possible to be present at any one time. And there was a delay to immunity, and we varied across those different constraints. So we ran 100,000 simulations for this algorithm to learn, and just to give you an idea of what this how this translates. So on the left is just an outbreak, just a simulated outbreak, and on the right you can see how that state of the outbreak translates into this 2-dimensional state space that we've generated. So you've got area of the outbreak along the right, where we're including all farms that have been controlled or infected, and the number of infected premises on the right. So the area of the outbreak sort of acts as a proxy for timing of the outbreak. We can't use calendar time because the outbreak doesn't really care if it's Tuesday or Wednesday. What we need to look at is some proxy for how the outbreak has progressed. So these are the policies that we get in the end. So once again, on the x-axis is the area of the outbreak, and on the y-axis is the number of infected premises. The plotted points are the optimal action that the algorithm has chosen as the best action to take in that particular state of the outbreak. The actions culling are in green, and vaccination are in pink and purple. Dark green is culling at 4 kilometres, and purple is vaccinating at 4 kilometres. So for one particular outbreak, the outbreak would take this sort of trajectory. So it would start from the same seeding conditions, and it'll progress through this state space, and the optimal action will change as it progresses through that state space. So the policies that we generate are state-dependent policies using this algorithm. So we can see from the policies that we've generated that vaccination was optimal for the outbreaks of a smaller area, but above a certain threshold it was better to use small-scale culling or vaccination. And this is something that's been discussed before, that vaccination is better to do early. In the previous talks we've seen at this meeting, but this is something that fell out of the algorithm. The algorithm discovered this. We didn't tell it this. The algorithm discovered this behavior itself. If we change the carcass constraint, we can see that culling becomes optimal as the constraint on carcasses is lifted, and there's a much, much smaller area of the state space that's explored. The outbreak is just getting stopped much more quickly. We looked at simulated performance experiments, and at the moment we're not getting, so we compared the reinforcement learning algorithm on the right. We simulated 1,000 times and see how well, what was the distribution of outbreak durations from those simulated outbreaks. That's that reinforcement learning algorithm on the right. And then we compared that against 4 different policies of the 4 actions we used, but not changing those actions through time, so static policies. And we didn't actually see that. So far, the reinforcement learning algorithm is not doing better than just culling at a very small radius or vaccinating at a large radius and not changing that through time. And there's a few computational reasons that I'm looking into at the moment to try and diagnose why it's not doing better, because we think it should do. And please come and talk to me afterwards if you're interested in hearing more about that. So in summary, reinforcement learning is a great technique for generating state-dependent control policies, and these can really capitalize upon this wealth of simulation models that are already existing in the field of foot and mouth control. These algorithms allow the search for non-intuitive control strategies, so we're not reliant on limiting ourselves to looking at control policies that we've thought up beforehand. The algorithm can discover some of those for us. We can also run this for different objectives. I showed it for an objective of minimizing outbreak duration, but we could look at it for a policy of minimizing livestock culled. And then we can get two different policies that we can overlay and look at concordance and discordance between the actions for these different objectives that might represent objectives of different stakeholders in the decision-making process. And finally, I've shown this for two state variables, so area of the outbreak and number of infected premises, and that was just for illustrative purposes. But I think using a small number of states is useful because it allows us to interpret it afterwards. It's not a black box algorithm. A lot of these artificial intelligence techniques are just black box algorithms, but the policy that we get at the end of it, we can give it to a human decision maker and say, does this make sense? We can give it to another modeling team and say, can you simulate this policy and do you get similar results? So in that way, it allows, these sort of methods allow artificial intelligence and modeling to once again augment human decision making and not be seen as a replacement for it. So thanks very much.
Very interesting.